Good morning, ladies and gentlemen. First of all, I would like to thank Mr. Jones, CEO of Southern Waste Information Exchange, SWIX, for allowing me to present this paper in this event. The title of my presentation is Catalytic Pyrolysis of Municipal Plastic Waste over Nano Catalyst for the production of transportation fuels. My co-author in this paper is Dr. Mousavi, my PhD student during the research. World production of plastic waste has been sharply increased, and only a small part of it has been recycled. The prediction for 2050 is 25 billion metric tons per year, from which only 30% will be recycled. So this is the main challenge for the environmental pollution in the world. There are two main conversion methods for waste polymers: mechanical techniques and chemical methods. For the mechanical techniques, we need to have pre-treatment of the waste before sending to the process, and there are some additives that have to be added to the system to improve the recyclable plastic waste. So there are stabilizers, plasticizers, fillers, chain extenders have to be added to the system. The chemical method, on the other hand, we have different techniques for different processes, such as pyrolysis. Pyrolysis can be thermal or catalytic pyrolysis. We have also gasification by air and steam, cracking in refinery units, which is fluid catalytic cracking or FCC unit, hydrocracking and pyrolysis reforming. The products can be extended from light olefins to BTX, fuels, waxes, and some chemicals, and finally hydrogen. Pyrolysis is one of the most suitable methods for conversion of plastic waste. There are some advantages for this system because there is no need for feedstock preparation. It's more economic because it has valuable products. It can be used directly for solid feedstock. It's non-sensitive feedstock purity and produce variety of fuels depending on the catalyst used. Pyrolysis conditions are normally between 400 to 500 degrees Celsius and in absence of oxygen. The products are liquid fuels such as gasoline, diesel, kerosene or jet fuel, and fuel gases, which are normally C1 to C4 hydrocarbons, and finally carbon residues as a final remaining products of the process. Feedstock can be extended from different type of polymers, LD and HDPE, low density and high density polyethylene, polypropylene, polystyrene, polyethylene, terephthalate, and PVC. These are the type of plastic waste that can be used for pyrolysis. In this research, we used only high density polyethylene at 2 grades, different densities, called as a light and heavy feedstock. Experimental conditions for pyrolysis depends on the type of pyrolysis. Normally, for thermal pyrolysis, we have higher temperature and we produce low quality products. It also requires recycling. For the catalytic pyrolysis, however, we have better quality products and less recycled materials. So the main parameters for the pyrolysis are temperature, pressure, and residence time, and the type of reactor also affect the product distribution. Type of catalyst which is used in this pyrolysis system are based on silice and aluminum. The ratio of silice to aluminum SiO2 to Al2O3 is between 3 to 27, and there are different type of catalysts that can be used. It depends on the products of the pyrolysis. Catalyst synthesis starts from mixing two main materials, which are NaOO2 and Na2SiO3, sodium trisilicate and sodium aluminate. We mix these two, we solve it with the deionized water, and then mix these two together to obtain a gel type solution. It is then it can be remain at room temperature for 24 hours. Then filter the solution and leaving in the oven for 120 degrees Celsius for 24 hours to dry out the catalyst, and finally calcined in oven at 550 degrees Celsius for 4 hours. Experimental setup includes the reactor. The reactor is tubular reactor made from alloy and sometimes from quartz. In this case, we used metal as a material of the reactor. The reactor is inside the furnace, electrical furnace, for heating up the reactor. Inert gas can be used for pyrolysis, and the product will be condensed in the condenser to separate liquid fuels from the non-condensable gases. Temperature of the reactor is controlled by PID controller, and there are some thermocouples at the beginning and end of the reactor and between the reactor, the middle of the reactor for temperature of the process. Obtain the range of temperature for pyrolysis, TGA analysis has been performed for HDPE, and as you see from the graph, at different heat rate from 10 to 50 degrees Celsius per minute, the range of temperature for dissociation of the or weight fraction of the feed is from 702 Kelvin to 779 Kelvin. So these are the two main temperature for the pyrolysis temperature. So we can find the temperature of the pyrolysis from this TGA analysis. This is exactly the same as 429 to 506 degrees Celsius, which is used as a pyrolysis reactor temperature. Let's look at some of the results. Influence of temperature and feed density on the fuel production for HDPE feedstock is shown in this figure. The temperature range is from 415 to 585 degrees Celsius, and the density is 959 to 967 kg per meter cube. As you see, by increasing the temperature, the efficiency, the liquid fuel efficiency has been increased, reaches to the maximum, and then decreases. The maximum efficiency goes from 89.1 to 95.3 based on the feed density. This figure shows the temperature effect of temperature and feedstock loading on the fuel production for HDPE. As you see, the same trend as temperature is shown for the loading. So by increasing the loading, the liquid fuel efficiency increases, reaches to the maximum, and then decreases again. Maximum production is performed at 509 degrees Celsius. The result of experimental analysis and experimental design analysis is shown in this plot. Plot shows experimental versus predicted results for the production of liquid fuels from HDPE, and the model which has been produced from the experimental design using CCD is shown in this slide. As you see, the R square values is very good. It's 96.26, and adjustable R square is 92.89, which shows the higher accuracy of the model. Gas analysis versus temperature is shown in this slide. As you see, the main gases are from C1 to C4, and the higher mole fractions are for propylene, propane, and methane, and ethane, and there are some low value C4 gases, plus the least value, which is for methane. Plot of experimental gas yield versus predicted values are shown in this slide. As you see, the R squared of 98.43 and adjustable R squared of 97, which shows the very good fitting of the data on the model. The model for gas yield is shown also at the bottom of the slide. The effect of catalyst on different useful products are shown here in this slide. As you see, more wax is produced for thermal catalyst, thermal pyrolysis. Without catalyst, the amount of the wax produced is very high, reaches to 48.72% of the product, while the gasoline amount is 23.86 for thermal. However, for zeolite and modified zeolite, we have better gasoline product, higher gasoline product, and less wax. The modified catalyst increases the amount of valuable fuel and has the lowest wax content. Octane number for the gasoline products are shown in this slide. As you see, for thermal pyrolysis, only 89.2 octane number can be reached, while for the zeolite Y and modified zeolite Y, 94.5 and 95.7 octane number can be obtained, which shows the gasoline grade as a premium for the product, while for the thermal pyrolysis only regular range of gasoline can be produced. The pyrolysis mechanism is still one of the most challenging topics based on the studies done by other researchers reported on the literature. This mechanism has been presented in this slide. As you see, the product, the feedstocks are different types of plastic waste, such as PP, polypropylene, PET, PS, polystyrene, HDPE, LDPE, and PVC. And the products are paraffins, isoparaffin, aromatics, olefin, naphthens. There are some flammable gases also produced as a result of the pyrolysis. So pyrolysis starts from polymer, then CaO, then oligomer, and then olefin, and finally carbon residues as a final product of the pyrolysis. There are different mechanisms for this conversion, from municipal plastic waste, dechlorination, random scission, chain and scission, beta scission, and finally going to the products. So as a conclusion, we can say that the maximum efficiency of gasoline without the use of catalyst are at 400 degrees Celsius, and the amount is 16.28. With zeolite catalyst, it has been increased to 28.71, and finally with modified zeolite catalyst, the efficiency of the gasoline production reaches to 37%. Jet fuel is one of the most valuable cut in this product. At temperature of 500 degrees Celsius, in thermal pyrolysis, the efficiency is only 9.77, while for the zeolite and modified zeolite catalyst, it's been increased to 20 and 30%. And finally, for the diesel as a heavy fuel at 450 degrees Celsius, in thermal catalytic pyrolysis with zeolite and modified zeolite type, we produce 25, 31.98 and 36.4 respectively, which is for the modified zeolite. Thank you for your attention, and I hope that this presentation was helpful, enough material for you to use it as a continuation of this research.